Okay, this is a continuation of our discussion of Chapter 4 in Wonnocott and Wonnocott's book on statistics. We just finished example 4.1, or problem 4.1. Let's look at 4.2. Simulate the experiment in problem 4.1 by using the random numbers in Appendix Table 1. Well, I don't have the Appendix Table 1 here. Even numbers equals heads, and odd numbers equals tails. But you could do this in Excel even more easily. You could use a formula like this. Rand generates a random number, multiply it between 0 and 1, multiply it by 100, gives you a number between 0 and 100, and you want then round that off with no decimal places, and you get numbers like this, and then you can just copy them down like that. And then he said maybe it's a good idea to copy this and paste it as values so they don't switch, because they might switch. And then see how they switched already. And then you could do if how do we do if even? So you could do a formula like this. You take the mod of this number, comma 2 means look for the remainder of that number when you divide by 2, and if it equals 0, then it's even, otherwise it's odd. So you get even and odd here. So you can generate easily even and odd here. So they said repeat this 50 times. Tabulate the frequency of x. So what was this? Sorry, even and odd. Instead of even and odd, I guess we could have boy and girl. So we'll let boy equal even and girl equal odd. And then we want to count, what is this? 3 children families. Actually, this doesn't quite make sense. It says even numbers equals heads, but this is not about heads. So I'm a little bit confused here. Well, actually, this seems not correct. So it doesn't seem to make the reference to problem 4.1 doesn't make sense. Maybe he's talking about some example 4.1. Well, I'm not sure about this actually. But you could, for example, if you wanted to simulate this, I guess you could take these, instead of even and odd, you could call them male and female or whatever, and then you could take the first 3 would be the first family, and the next 3 would be the next family, and the next 3 would be the next family, and so on. So you could simulate checking different families, and then you could count how many males and how many females you had in each family, and then you could get a relative frequency distribution for what do they want here? For how many times you have no males or no girls, 1 girl, 2 girls, and 3 girls. So you could get the relative frequency distribution. You could certainly calculate the mean for how many children you had, and you could calculate the variance. Okay, I'll leave that discussion at that, but it seems to be some mix-up here. This one says if you did it many times, what would the calculated probabilities tend to, or what would the calculated quantities tend to? And they would tend to the probabilities, which are maybe not these, because he's assuming 50-50, but something like these. He's assuming 50-50, and in these problems below, he's assuming boys and girls are equally likely, but he didn't. But these values are not for that scenario. So anyway, it'd be close to these though. Okay, problem 4-4. A salesperson for a large pharmaceutical company makes 3 calls per year on a drugstore, with the chance of a sale each time being 80%. Let X denote the total number of sales in a year. So obviously, again, how many sales, if X is the number of sales, what are the possible values for X? And these are the possible values for x, because you're making only 3 calls per year. So you might get no sales, you might get 1, 2, or 3 sales. Tabulate and graph the probability distribution for x. So what he wants you to do is figure out what's the probability that x is 0, 1, 2, or 3. So this is kind of the same picture as this. But here, the first call is not whether he makes a sale or not, but whether there's a boy or a girl. But so you could have sale or not sale here, so like S or N, S or N, S or N. And then what would be the probability of SSS, right, and SSN, and so on? You'd have the same, basically the same set of outcomes here. You'd have different probabilities here because the probability of S is 0.8, and the probability of N is 0.2, and not 50-50 or anything near 50-50. But you'd get the same thing, same kind of picture. And then you could calculate the probabilities for these different values of x, where x is the number of sales. So do that. So do this, and then what is the chance of at least 2 sales? Means the probability that x is 2 or greater than or equal to 2. Okay, repeat problem 4.4 under the different assumption that nothing succeeds like success. Specifically, while the chance of a sale on the first call is still 80%, the chance of a sale on later calls depends on what happened on the previous call, being 90% if the previous call was a sale and 40% if the previous call was no sale. So now you don't get to use this rule. You don't get to use this rule anymore, the probability of A and B and C. In other words, this is independent, but they're not allowed to use independent now. So we have to use a conditional probability. So we'd like to use this rule, that they're independent, but they're not. So instead we have to use this rule. Now where does this come from? You should know that. What's the definition of this thing here? This is the probability of A given B is what? The probability of A intersect B, or A and B, divided by the probability of B. So I can bring that probability of B over here, and I get that. So I have to use this rule, but you have to sort of use it cleverly, because it's not just 2 events, it's 3, so you have to figure out how to use it. But anyway, instead of writing this, which we'd like to have written, he said no, we have conditional relationships between the probabilities, so we can't do that. Okay, so I'll leave that for you to work on. Okay, and we'll start section 4-2 next.